the problem of automatically finding such an invariant is the problem that we're considering. The main contributions of this work are first induction duality, which is a new mathematical connection between execution traces and incremental induction proofs. And second, final dual Houdini, which is a new algorithm that we obtained from the mathematical duality. We start by deriving dual Houdini by starting with the Houdini algorithm and mechanically reflecting it through the induction duality to derive dual Houdini. And then by combining Houdini with dual Houdini, we obtain a symmetric prime dual invariant inference algorithm that has nice theoretical properties, including some termination and progress properties, and also has some promising empirical results for distributed protocols like the one I showed. All right. So to get a little more concrete, I want to use this illustrative example of a program that manipulates three variables, A, B, and C. They are all initially zero. And on each iteration of the loop, we use this simultaneous assignment to add B to A, C to B, and add 1 to C. And we want to prove that A is greater or equal to 0 in this program. Now, one way to understand this program is to think of the graph of states and transitions, where we start in a state where all the particles are 0, and with one iteration, we can get to this state where A and B are 0 and C is 1, and so on. And using this graph, we can, of course, define the set of reachable states. But the graph also includes states that are not reachable. For example, these states and this transition between them. And one way to make sense of a transition between non-reachable states is as an implication, saying, well, if this state is reachable, then this state is reachable. And in order to prove that A is non-negative in this program, the standard way to do it is with an inductive invariant. For example, for this program, we need this loop invariant that both A, B, and C are all greater or equal to 0. If we just use A greater or equal to 0, it is not inductive. But another way to view proof by induction is to view it as an incremental process that progresses in a stepwise manner. And we can use this notion to also define a graph. So we will start from true. And then for this example, with one induction step, we can prove that C is non-negative. This is inductive just by itself. Then if we assume that C is non-negative is an invariant of this program, then we can prove by another induction step that B is non-negative. And with another induction step, we can prove that A is non-negative. Now, this graph will also include predicates that are not invariants and induction steps between them. For example, for this program, we have a step from B equals 0 to A equals 0. And one way to make sense of this step is that if you were to believe that B equals 0 is an invariant of this program, then by induction, if you consider the program, you should also believe that A equals 0 is an invariant. Now, many existing algorithms for verification and model checking and in program analysis and invariant inference consider states and transitions and predicates and induction, but and there is some notion of a primal dual interaction going on, but this is not formalized and it's definitely not symmetric. And our goal with this work is to develop a formally symmetric primal dual algorithm that explores these two terms. So the first step to do that is to actually see that how we formally define these two graphs in a way that is symmetric. So we are going to define to precisely define these edges, these induction steps, and the intuition is going to be that a step should mean that if P is invariant, then Q is by induction also invariant. Notice that P and Q here don't necessarily have to be inductive invariants. And our formal definition is going to be this: that if we start in a state that satisfies both P and Q, and make a transition to a state that satisfies P, this state should also satisfy Q. We can also write this using the Willis precondition over the loop mapping. But the best way to understand this is visually. So we have an induction step from P to Q. If for every transition from state S to state T, such that the pre-state S satisfies both P and Q, and the post-state satisfies P, then T should satisfy Q. Now, if you believe P to be an invariant, then show you the property that it implies for paths, which really justifies taking its definition. It has the definition of incremental induction. So if we have two graphs that are related by this pattern, and we have two paths in this graph, such that the starting point of this path is related, satisfies all of these points. Say the initial state here is going to satisfy all the predicates that we're going to use. We only use predicates that are satisfied by the initial state. And also the starting point here is related to all of the points here. So we start our proofs from true, which is the predicate that is known to known states. Then every point here has to satisfy every point here. And this is exactly what we want, that anything that is reachable from true here is satisfied by anything reachable from the initial state. And the proof is very easy. It's by simultaneous induction on both of the paths. So if we assume by contradiction that there is some violation of this, and we take the minimum one, it cannot use one of the initial points, so there must be two edges. And then by minimality, we get that this connection must hold, and also this one, and also this one. And now we get the contradiction to this. All right. So we have established a symmetric connection between executions and incremental induction, and that's very nice. But there is still an important difference that we have to address before we can derive new algorithms. And that is a phenomenon that happens over here with proofs, that every incremental proof can actually be contracted to a single edge. For example, we also have a single edge from true to the conjunction of A, B, and C being non-negative for our example program. And this makes this graph, the edges in this graph, too powerful. Also, it makes the paths here a little bit degenerate because anything that is provable with any path is also provable with the path of type 1. And it also makes algorithmically dealing with this graph too difficult. So this motivates our next step, in which we're going to use slightly more complicated definitions, where the graphs are going to be over finite sets of states and finite sets of predicates. So we're going to start with, and we're going to define four sets of edges. So we're going to start with the simplest one, this what we will call E, that represents transition. We will go from a set of states S to a set of states that include another state. If this state is one of the co-states of this set, and this includes also a new initial state. And now we will use our definition to define a graph over sets of predicates, which will just be all the edges here that respect this connection with this graph. So this graph is induced by this graph or derived. But as we said, this graph is too powerful. We're calling it E prime omega. Now we're going to take a subset of it where we add at most k new predicates. So k is a fixed parameter for this construction. And in this graph, it's just a subset of this set of edges where we add at most k predicates at each time. So now for this graph, the edges are not too powerful. We don't have this property that paths can be contracted to a single step. And it makes it now interesting to do proofs over paths in this graph. And we obtain that by applying our construction again to this graph this time to obtain another graph over sets of states, which we just derived using this definition from this graph, and we call this one E omega. So let's understand these four sets of edges a bit more. First of all, it turns out that this set of edges is a superset of this set of edges, same as here. And the things that are reachable in this graph are, well, they represent the reachable states. Things that you can reach here, and as we've said, anything you can reach by one step, these are the inductive environments. Things that you can reach here, these are what we call k-provable predicates. These are predicates that you can prove with an incremental induction proof that where at each step you get at most k predicates. And if you want to understand this graph, we call it dual inductive. You can the sets of states you can get here are sets of states that form an inductive invariant for this graph. Namely, a set of states here is dual inductive if it is satisfied by every k So this graph is a way to provide an upper bound of what you can reach here, exactly the same as this graph is providing an upper bound for what you can reach here. Now, this structure is perfectly symmetric if you switch the role of vertices of states and predicates and change the primed and unprimed symbols. And this is the new induction duality that we are going to use to derive new algorithms. And the fact that it's symmetric is crucial for deriving new algorithms. That's what we just see. All right. So let me now show you how we derive dual Houdini. So we start with Houdini, which is a very simple algorithm. It gets a set of predicates, and it finds its largest subset that is inductive using a simple fixed point iteration. So at each iteration, we ask, is there a counterexample to induction for our current set of predicates, which is a transition from a state that satisfies the set to a state that violates the set? And if yes, we prune our set of predicates. So for example, if we start with these four predicates, we might first find a transition from a state that satisfies all of them to a transition that violates P2, and we will eliminate P2. And maybe then we will find another transition from a state that satisfies all of these three predicates and violates P1. And maybe then we reach the fixed point, and the conjunction of P3 and P4 is an inductive defined. So now we mechanically reflect this algorithm across our induction duality, and we obtain this algorithm. So let's try to make sense of it. The input here is a set of states. And in the fixed point iteration, we search for what we call a dual counterexample to induction, or a dual CTI. And this is a bounded induction step, PQ. So in Q, we can have at most k new predicates. This makes the search for such dual CTIs actually practical, such that this set of states is satisfied by the starting predicate, but it's violated by the target predicate. And then we similarly prune the set of states. So for example, if we start with this set of states, we might find an induction step from P1 to P2 where P1 satisfies all of them, but P3 violates and P2, sorry, violates S1. And then we might find another induction step and prune the states again. And then we're going to reach our fixed point. What this fixed point means is exactly this dual inductive set of states. So the fixed point that we get here, they cannot be ruled out by any k-bounded incremental induction. All right. So now the last conceptual step is to realize that Houdini discovers new states using these counterexamples to induction, and dual Houdini discovers new predicates via these dual counterexamples to induction, and we can combine them to obtain a primal dual infinite inference algorithm. We discover new states using Houdini. We feed those into dual Houdini, which discovers new predicates, and then we feed those into Houdini, and so on. And this algorithm is completely symmetric across the induction block. And this is our primal dual Houdini algorithm. More details about it are in the paper, of course. And it has some nice theoretical properties. First of all, exploration, that every iteration must discover a new state or and a new predicate. It can get stuck in some deadlock where all the CTIs and dual CTIs use already existing states and predicates. And a more interesting property that is very challenging to prove and has a very nice proof is that it empirical evaluation. We only have an evaluation for k equals 1 so far, but it actually turns out to be very useful. This partition, of course. You see here a comparison between Farm and Dorothea and several state-of-the-art algorithms, and most of them based on IC3. And we think that it's very nice and very promising that a completely fresh algorithm that came out of this mathematical duality is actually competitive. You see that for some examples it uniquely solves them, for some examples that are challenging it solves them along with another tool. And you also see, interestingly, that some easy examples, for example, this one is very easy, it doesn't solve. And the reason is that this example requires a k that is much larger than 1 to prove it. So we actually can understand the success or failure of Cramer-Dorothini by considering the theory on which it's based, which is also nice. And another important conclusion from the evaluation is that implementing a solver for these dual CPIs is actually practical. All right, so let me conclude. Our goal was to obtain a symmetric prime and dual inference algorithm, and the key idea for them was to consider bounded incremental induction. This allows us to formalize a symmetric connection between executions and bounded proofs, which we call induction duality, and also to derive prime and dual Dini, which is a fully symmetric prime and dual algorithm with interesting theoretical properties that rely on the prime and dual interaction and promising results for distributed protocols. I briefly mentioned a couple of very natural future directions for this. First, to apply to more domains beyond distributed protocols. And second, to apply this formalism to obtain prime and dual versions of more advanced algorithms beyond Houdini. And as a teaser for the paper, I want to show you this figure, which depicts the operation of prime and dual Houdini. So the left side here is the lattice of states, and the right-hand side is the lattice of predicates. And the only thing I want to tell you about this figure right now is that it has two symmetries. If you relate the two sides with a vertical reflection, it corresponds to a classical Galois connection between states and predicates from abstract interpretation theory. And if you relate them by horizontal reflection, it corresponds to the new induction duality. And I find that very interesting. Thank you for listening, and I'm happy to take
Thank you.
questions.
Thank you very much. Other questions from the audience?
I'm only seeing my slides, so someone has to.
Yeah, okay. Other question from outside? Yes. For evaluation of your theoretical result, why did you choose distributed protocol specifically?
That's an interesting question. So the reason is practical. I was working on verification of distributed protocols before and writing their invariants by hand, and I actually ended up with these ideas by thinking of how we can automate the discovery of such invariants.
Good.
So, yeah. But I will also say that this is now a very active area. All of these, or most, I should say, let's say all of these algorithms are from the past couple of years, and there is very nice progress in finding these invariants, which are complicated. They have a lot of modifiers, and I think it's very challenging and nice.
Okay. I have one question. I mean, you mentioned that there may be a state predicate explosion, and it looks, in particular, your last observation that abstract interpretation can work well in this context. Can you comment more on that observation you made at the end with that two nice pictures on the conclusion slide?
Yeah, so I think a better understanding of the connection between abstract interpretation theory and this induction duality, I think this is something that I would like to do. We have some understanding in the paper and with this figure. I'm not sure how it relates to the explosion. So the fact that this algorithm can diverge comes from the fact that when it finds a new predicate or a new state, if it quickly determines that the predicate is violated by which of the state or that it's invariant, and similarly for a state, if it quickly determines that it's reachable or it quickly determines that it is k-abstractly reachable, meaning that it satisfies all the k-protocol predicates, then the algorithm kind of manages and doesn't explode, but otherwise it could learn more states and more predicates and just explode exponentially. I mean, let me just speculate that this
Okay. No other questions? Okay, we thank the speaker again. Thank you, Oded. Bye.